Yes. So in this class, we will design a flat slab. I have given the theory concepts in the last two video classes. So the problem runs like this: design the interior panel of a large single-story warehouse flat slab roof with a panel size of 6 meter by 6 meter. Supported by columns of size 500 mm by 500 mm, that is square column. So height of the columns is 5 meters. Live load is 3 kg per meter square. Weight of finishes is 2.5 kg per meter square. So materials used are M20 concrete and Fe415 steel. So this is the standard type of problem. So here the columns are square columns. And the panel size is 6 meter by 6 meter. It is the interior panel. So we have to refer the page number 53 to 60 of IS 456 for design of flat slabs. So in the examination, this code will be provided. So that is why I have to note down the page numbers of the code. So now I will do it in steps. So the first step is we have to assume the thickness of slab. So thickness of slab as per the code, it is minimum is 125 mm. Minimum thickness is 125 mm. So this we should remember. If you get less than 125, you have to provide a minimum 125 mm. So now, what we do here is, this thickness normally is calculated based on L by D ratio. Based on L by D ratio, which is available in L by D ratio, where L is the span and D is the effective depth or effective thickness of the slab. So page number 39 in code, page number 39, he has given the L by D ratio for the slabs or the beams. So you can refer that page number 39. What it tells is, for two-way slabs, you can see that it is available in class 24.1. Page number 39, class 24.1. He has given the L by D ratio. For two-way slabs of shorter spans up to 3.5 meter with mild steel reinforcement, of course, it is with mild steel reinforcement he has given up to loading of 3 kg per meter square. When you are using Fe415 steel, that value is little bit reduced. So we have to multiply that value by 0.8. That also he has given. That means here in this case, what happens here is the value for continuous slabs is 40. For continuous slabs it is 40, it is given there. So you have to treat this flat slab as a continuous slab because it is supported by columns. We have to take it as continuous slab. So that value of 40 should be multiplied by 0.8. So because we are using Fe415 steel. So what we can do here is this L by D ratio, we can take it as 40 into 0.8. So this 0.8 because we are using Fe415 steel. If it is mild steel, we have to take it as 40. If it is Fe415 steel, we can multiply it by 0.8 so that it becomes 32. 32. L by D ratio becomes 32 now. Now the value of D you can fix from this. So we have got L by D is equal to 32 now. So therefore D is equal to L by 32. L is 6 meters. Please note that the panel is of size 6 meter by 6 meter. So 6 meter means 6000 mm divided by 32. So this value comes out to be
187.5.
187.5. 187.5. So this is effective thickness. Now we have to assume cover and also diameter of the bar. If you assume 20 mm cover and 12 mm diameter bar, you can find out the total thickness. Assuming 20 mm cover and 12 mm. Normally 12 mm bars are used, dia bars. So your total depth, so overall depth capital D becomes small d, that is 187.5 plus 20 clear cover, suppose it is clear cover, plus half of the diameter, that is 12 divided by 2. So this is how we have to calculate the overall depth. So it becomes how much? 26 plus this 213.5. 213.5. So this is what we got now, 213.5 mm. Now let us provide a depth of 215. Okay. So this is the required depth. So provide, we will round it off. D is equal to 215 mm. So then small d becomes how much? 215 total depth minus clear cover minus diameter of the bar. So it becomes how much? 189 mm. So this is the 189 mm is the effective depth we are going to give. So definitely this is greater than 125. Okay. So no problem. So minimum depth required is 125. So we are providing 189 effective depth. Okay. Effective is only 189 and overall depth 215. So you know that overall depth is calculated like this. So this is overall depth capital D. That you have filled in RCC. So if you are providing reinforcement like this, okay, if you are providing reinforcement like this with proper spacing, so then this is your effective depth, correct? Small d is this. So this is your 12 mm diameter, means this becomes 6 mm and this is clear cover. So in this case this is 6 mm, this is 20 mm. So overall depth is 215 mm. So small d will be 189. This is how the reinforcement is provided. So now the second step, we have to calculate the size of the drop panel. So second step, first step we have fixed the thickness. Second step, size of drop panel. So I have explained in the last two lectures about with a sketch about the components of a flat slab. So if this is the slab, so you are going to provide a drop panel here, like this. So this is called as a drop panel, this portion. So now we have to fix the size of this drop panel. This is the flat slab. So this is drop panel we have to provide. So let us fix the size of the drop panel. So once again, as per class 31.2.2 of the code, class 31.2.2 of the code, page number I will give you, page number 53. Page number 53 it is there. So page numbers are very important. You can directly refer the code. Page number 53, it is available. Drop panel should not be less than. Drop panel should not be less than span divided by 3. According to that, this is the length of the drop panel. Okay, this should not be less than L by 3. So here L is 6000 mm, 6 meters. So that is 2000 mm. So it should not be less than 2000 mm. Say I will provide 3000. So let us provide 3000 mm, that is 3 meters drop panel. This is the drop panel, 3 meters. So they are providing 3 meters drop panel. Then minimum depth of drop panel. So this one, this is minimum depth of drop panel. I will take it as ds. So ds will be, so minimum depth ds is equal to 1/4 of this is ds, sorry, this is ds. this overall, this depth of slab is ds, that is d, in our case it is d. What is the value of d? 250. Or I can write it as d only. So d is equal to 215 mm. So this value, this is your drop panel. I can take this drop panel thickness as ds. So this is ds. ds is 1/4 of d. So 1/4 of d is 1/4 of 215. So what is the value? 1/4 of 215 is 53.75. Correct? 53.75. That is the minimum depth. So you round it up to 60. Say 60. So we will provide, therefore ds is equal to 60 mm. 60 mm we will provide. So now this is fixed. So this is 60 mm. So this is 3 meter. This is 60 mm. This is 215 mm. So this is the dimension of the drop panel. So therefore, now the overall drop panel dimensions. It's a square panel. So 3000 mm by 3000 mm by 60 mm. Okay. Got it? This is the value. So when you see from the top, so what happens? Column will be there here like this. This column size is 500 mm by 500 mm. That he has given 500 by 500. Whereas this drop panel will be like this. Drop panel will be like this. This drop panel size is 3000 by 3000. That's what I mean. Okay. So this is the plan. This is in plan. It looks like this. So now drop panel dimensions are over. Next step is, that means your total depth of drop panel now it becomes, that means total depth means this total depth 215 plus 60. So total depth of drop panel is equal to 215 plus 60, 275 mm. That is the total depth. So this should be greater than 1.25 times d. As per the code, this should be greater than 1.25 times d. That is 1.25 to 215. It will be greater than that. How much is that? 1.25 times 215. I think it comes to 269. So it is greater. So no problem. 275 we got. So therefore it is okay. Okay. So this is about the fixing the dimensions of the drop panel. So therefore the width of column strip now, it becomes now width of column strip and middle strip. They are equal. Is equal to width of middle strip. So in the first lecture, first and second lectures, I have explained about column strip and middle strip, all those things. So width of column strip and middle strip, you can take it as L by 2, that is it is equal to 6000 divided by 2, 3000 mm. So 3000 mm is the width of column strip and middle strip. So about this column strip and middle strip, I have explained in the last two lectures how we had to take that. This is the column. These two are the columns. So what happens? This drop panel will be there here. This sketch I have explained in the first two lectures. So this is how it looks like. Okay, these are the columns. This is the drop panel. Of course, we are not providing any column head here. We are providing only drop because the thing is mentioned. We can provide only drop here. So here we have to divide this into strips, 3 strips. So those 3 strips we have to take it as middle strip. So middle strip will be here. So this becomes the middle strip, and these two becomes the columns. These two become the columns. So all this I have explained in the earlier 2 lectures. Now the width of middle strip and column strip, they are normally taken as L by 2. That is, L is here 6000 mm. That is the panel size. Divided by 2 means it becomes 3000 mm. So now that is step 2. Now step 3, we have to calculate the loads. So dimensioning of the slab, flat slab and the drop panel. So they form the first step. First and second steps. Now we have to calculate the loads. So normally he will give the live load and finished load. We have to add dead load to that. So third step is calculation of loads. Calculation of loads. So first we will take up the given loads. So he has given the live load as 3 kN per meter square, finishes as 2.5. So let us write down that. Live load has given 3 kN per meter square for the warehouse, and finished load 2.5 kN per meter square. They are slab loads. So we have to calculate the dead load now. For calculating dead load, let us calculate the self weight of slab. Self weight of slab. Self weight of slab. So overall thickness of the slab is 215 mm. So therefore in meters it is 0.125. Correct? 0.215 into density I will take 25 kN per meter cube. So it comes to 5.375 kN per meter square. That is the dead load in the middle strip actually. This is in the middle strip. Because the column strip drop will be there. Correct? Yes. So this is in the middle strip. E portion, only in this portion. In this portion, depth is 215 mm. Whereas in this column strip portion, so the depth becomes how much? 400. 275. That is 215 plus 60. 275. It becomes 275. Be careful. So we are calculating in the middle strip. So here at drops extra load will be there. So it becomes dead load due to thickness of slab at drops. Thickness of slab at drops. So extra thickness we are giving how much? We are giving 60 mm. So 60 mm means 0.06 meter into 25. So 0.06 into 25 means it comes up to 1.5 kN per meter square. 1.5 kN per meter square. Now we have to add all the things here. So to get the total load. So we add all the things. So it is 3 plus 2.5 plus 5.375 plus 1.5. How much it is? 12.375 kN per meter square. Correct?
Yes, sir.
12.375 kN per meter square. Now this is actually working load. So factor load we have to calculate. Factor load is 1.5 times this. 1.5 times 12.37. So it comes out to be 18.56 kilonewton per meter. So this is actually WU, we call it as ultimate load. So that is the factored load, because we are using the limit state method of design. Now in flat slabs, we have to calculate what is called as clear span, which is denoted by L. This clear span is given by L minus here whatever size of the column is there, L minus size of column, that we have to take. Size of column. So what is size of column here? The L is 6000 mm. Size of column is 500 mm. So 5500 mm, or it is 5.5 meters. So clear span in case of flat slab is this. Okay. So we have to deduct that. So we have to deduct this portion. So this is your in this I can show here like this. This is your L. So L minus size of column. Okay, this is the clear span. Now the design load, we have to calculate. Factor load is different, design load is different. Design load is given by W, capital W I will call it as WU into L2 into LL. This is the formula we have to use. WU is this value, factored value 18.56 into L2 is 6 meters. Here L1 and L2, they are same here, 6 meter by 6 meter. If it is a rectangular panel, then you have to take the higher value. Since if it is square panel, you have to give it will be same. So L1 and L2 will be same into 5.5. This is the design load we have to take. 612.51 kilonewton. This is in kilonewtons.
Yes, sir.
So this is in kilonewton per meter square. This is in meter. This is in meter. Therefore, the value becomes 612.48 or 5. Now this is about the calculation of loads. Next step is bending moment. Calculation of bending moment. Fourth step. Calculation of bending moment. So here, so this is called as direct method. So bending moment is given by so step number 4, calculation of BO. So here what happens, design bending moment, MO, I call it as MO, design bending moment is equal to MO. So it is given in class 31.4.2.2 of page 55 in the code, page 55. Page 55 in the code. It is given by WLN by 8. So this is the formula used to find the design bending moment. So W here is 612.5 into Ln is 5.5 divided by 8.
421.1.
421.1 kilonewton meter unit. 421.1 kilonewton meter. So this bending moment is distributed into positive and negative bending moments. That is as per the same in the same page he has given as per class 31.432 in the same page page 55 only. So this bending moment is divided into positive and negative bending moments. So total negative bending moment. So negative bending moment. Total negative bending moment is taken as 65% of MO. That is 0.65 times MO. That is 0.65 into 421.1. So the value becomes 273.7 kilonewton meter. Then the remaining bending moment is the positive bending moment. Total positive bending moment is 35%. That is 0.35. This is 65%. This is 35%. M naught. So 0.35 into 421.1, which comes out to be 147.4 kilonewton. So we have to design the reinforcement. Now next, final moments, they are distributed now. These moments are distributed. These moments are distributed as per the class. They are not final. As per class 31.551 and 31.553. Class 31.553, page number 57. So that's why these page numbers are very important. As per this class, these moments are distributed now. So they are distributed into what we say column strip and middle strip. Okay. So negative moment I will write like this. The negative bending moment is taken as in the column strip. I will write like this: column strip in kilonewton meter and middle strip in kilonewton meter. Actually, moment in the column strip will be more than the moment in the middle strip. Okay. So because load will be acting here on the column, so that's why moment here will be more. Columns will carry the column strip moments will be more. So negative bending moment is once again taken as 75%. 0.75 times 273.7. What is the value? 205.3. Correct?
Yes.
So this is the column strip moment. Similarly, positive bending moment is taken as 60% of it. That is 0.6 times 147.4. So positive bending moment we have got 147, negative moment we have got 273.7. So 60% of this. So these two are available in this class. That's why I will page number. So this value is 88.4. Now whatever remaining is there, that comes in this middle strip. So out of 273.7, 205.3 is taken by column strip. remaining means 273.7 minus 205.3. That is taken by the middle strip. So reinforcements are different here. Middle strip moment is different, column strip moment is different. So this difference you have to take. Out of 273.7, 205.3 is taken by column strip. Remaining will be taken by middle strip. So what is this value? 68.4. Okay. Similarly here, 147.4 minus 88.4. It comes to
58.96. 59.
59. So these are the moments we have to take finally for the middle strip. These are the moments we have to take for the column strips. Okay. For these moments we have to design the reinforcement. 12 mm diameter bar we have assumed, So we have to design the reinforcement for these moments. Please note that for negative bending moment, we are providing reinforcement at the top. For positive bending moment, we are providing reinforcement at the bottom. So this I have explained in the last 2 lectures. Negative bending moment, reinforcement at top of slab. Whereas for positive bending moment, reinforcement at bottom. Sagging and hogging. For sagging bending moment, that is taken as positive. Reinforcement is provided at the bottom. For hogging bending moment, negative bending moment, reinforcement is provided at the top of the slab. Now, what we have to do here is, before going for the calculation of reinforcement, we have to check whether the depth provided is sufficient or not, based on the moment criteria. So, based on the bending moment criteria, whether the depth provided is sufficient or not. So, for that, we have to use the equation which is given in the code, effective depth calculation. So, check for effective depth. Next. So, initially we have assumed some depth. Now, after finding all the bending moments, we have to take the maximum value of the bending moment. Among these 4, which is the maximum value? 205.3. So, that value of bending moment we have to take, and we have to check whether the depth provided is sufficient. So, this equation we can get from the code. So, step number 5, check for effective depth or check for depth. So, this check for depth is done taking maximum bending moment among those 4, numerically maximum. Okay, so numerically maximum is 205.3. So, mu is 205.3 kilonewton meter. Now, the equation is like this: mu is equal to, so this is the equation available in the code. So, you can refer the page number I have not written here. Mu is equal to 0.138 FCK into BD square. So, this is the equation we have to use. Here we have to calculate D here. So, mu is 205.3. You can just take it. So, D becomes down here. If you want D will be mu divided by 0.138 FCK into B under root. Correct? This is the formula. So, this 0.138 is for Fe 405 steel. Now, substitute the values. You know the grade of concrete as M20. So, put FCK is equal to 20, and this B value you have to take 3000 because that's split by. So, B is 3000 here, 3000 mm. Column strip and middle strip lengths are 3000 mm. FCK is 20 Newton per mm square. And MU value is this. Now, you substitute and simplify. So, mu I will take 205.3 into 10 power 6 because the value I have to put in Newton millimeter divided by 0.138 into FCK is 20 into B is 3000. So, square root of this is the value of B. So, this 20 is in Newton per mm square, this is in millimeter. So, finally, if you simplify, you are going to get in millimeters. So, if you simplify that, I think you will get 141 mm. This is D required based on bending moment criteria. But what is the D provided? So, D provided here is totally 275. Total depth is provided. So, D provided at a drop. This is calculated drop because we have taken the column strip, you know. So this total depth we have to take. From this total depth, we have to deduct the cover. Then we have to deduct half the diameter of the bar. So this is the value. 275 minus 26, it comes out to be 249. So provided is 249, required is 141. So same. Therefore, it is not greater than 141. So therefore, same. Got it? So initially we are assuming some depth based on L by D ratio. Then after calculating all the moments, loads and moments, we have to take the maximum bending moment and we have to check whether the depth provided is sufficient based on that maximum bending moment. So you have to get the value D provided based on required based on moment value is 141, but provided is more. So when provided is more, then it is safe. If provided is less, then we have to redesign. We have to increase the depth and once again you have to calculate the load, dead load, everything. Dead load will change. When you increase the thickness, dead load will change. That is why design has got two steps, preliminary design and final design. So in preliminary design, so we are assuming the dimensions based on some criteria, here L by D criteria. Then final design means after getting all the moments, we have to check whether the depth assumed in the beginning is sufficient to take care of that bending moment. So now in this case, it is okay. Next step is we have to check for punching shear, because normally here what happens in the case of drop, it is in the case of just like in the case of footings, we have to check for punching shear. That is another important thing. Even though shear is not a major criteria in flat slab, but we have to check for punching shear. So that also we will do. So step number 6, check for punching shear or two-way shear. It is also called as two-way shear. Check for punching shear. So 6th step, check for punching shear. So two-way shear. It is also called as two-way shear. So there are two types of shears, one-way shear and two-way shear. One-way shear is also called as beam shear, whereas two-way shear is called as punching shear. So this can be done just like in the case of footing. So for a footing we are going to do this punching shear check. Similar lines we have to do for flat slab also. So here the critical section is taken as critical section is taken at a distance d by 2, small d by 2, from the face of column. From the face of column. At a distance d by 2 from the face of column. So here the value of d by 2 is 249 divided by 2, correct? D by 2 is 249 divided by 2, which is 124.5. Okay? So we are calculating at the column strip now. Now what happens here? This is the column. Now you show the critical section. So this column dimension is 500 mm by 500 mm. This punching shear we have to calculate at a distance of, these are the faces of the column. So this d by 2, that is 124.5 mm this side as well as this side. Okay. Now we have to take this section like this. This is the section, critical section or punching shear. Okay. From the face of the column, we have to take d by 2 distance. So we are checking. So load is acting like this. Whether any shear is there, punching shear is there from all the 4 sides. That we have to check now. Now this becomes the critical section now. This perimeter. Critical section. Now there is a procedure to, it is given in page number 59 of course, page number 59, check for shear. Normally whatever we do for footings, same procedure is done here also. So for that what we calculate here is perimeter we have to calculate first, perimeter of the critical section. So what is the perimeter? Perimeter of critical section, it is a square section. So 4 times, what is this? How much is total of this? Can you tell me? 500 plus 249, correct alva? 500 plus 249, 749,
Yes.
749 this side, 749 this side. So 4 times 749, correct? Perimeter means this. So it comes to how much?
2,996.
749. 2,000?
996.
996 mm.
Yes.
That is the perimeter of the section. Next we have to calculate what is called as shear force on this plane. So what is the shear force on this plane? We have to calculate shear force on this plane. So shear force on this plane is given by whatever load you have got earlier. What was the load? WU. So sorry, not WU, W. W was how much? 18 WU. Somebody. You take WU. 18.56. WU into that area we have to take. See here, this area becomes what happens? Total area is L by L. So you have to understand here, this is L. Panel length is L here. This is also L. So this is 6 meters. This is 6 meters. Okay. Among this, we have to deduct this one. So we are calculating only for this area. Actually, this is how much? 749 mm means it comes out to be 0.749 meter. This is also 0.749 meter. Now what we are doing is we are calculating the shear force on this plane. So your total panel is 6 meter by 6 meter. In that you have to deduct this. So area becomes now 6 into 6 minus 0.749 into 0.7. So this is what we have to do.
35.4.
Now 18.56, this you have to take. So this is 18.56, we have calculated earlier. Into what is this value? 30?
Total.
Or you can calculate this I can write it as 36 minus 0.749 square. Yeah, this is the shear force of the plane. 650 something. So the shear force I can take it as VU. Evaluation, what is this value? 600 something.
Minus 35 into 18.56. 657.
657 kilonewton. This is a kilonewton. 657. So this is the shear force. Now we have to calculate what is called as nominal shear stress. So the shear force is denoted as VU. So all this we are doing in RCC also, in beam design and slab design. The same procedure is followed to check for shear. So what we are doing is we are check for shear, that's all. Now we are calculating nominal shear stress. In page number 59 in the code, page number 59 in the code, he has given one equation for nominal shear stress. Nominal shear stress is given by VU by BD. VU by BD. That is the formula. VU by BD. So V here is this value, 657 into 10 power 3, because I have to take it in newtons, divided by B is that perimeter. So this is B. Please note that this value is B. 2996 into effective depth. Effective depth in this case is how much? 249. Yes. This is in millimeter square. So just simplify this. You get nominal shear stress. How much?
0.88.
0.88 Newton per mm square. So nominal shear stress we are getting 0.88 Newton per mm square. Millimeter square. This is the nominal shear stress. Now what we have to do is we have to calculate what is called shear strength of concrete. Actually this is toe. Next, concrete, shear strength of concrete. Shear strength of concrete, we have to calculate, we have to compare that value with this. Shear strength of concrete as per class 3163 in page number 59. So page number 59, if you open the code, so all these designs are similar as that in RCC. So shear strength, what permissible shear stress he has given, class 3163. I will take class 3163, page number 59. So shear strength of concrete is given by Ks into tau c. That is the formula. Ks into tau c. Ks into tau c. Here Ks is given by 0.25 plus beta c. Ks is given, everything is there, plus beta c. 0.25 plus 0.5 plus beta c, not 0.25, 0.5 plus beta c. So this value, actually here beta c is taken as 1. So he has given about beta c being the ratio of short side to long side of the column or capital, which is equal to 1 here. So therefore beta c is 1 here. In this case 500 mm by 500 mm is the column dimensions. So beta c is 1 here. Therefore Ks becomes how much?
0.5.
Ks becomes
0.5.
0.5. 0.5 plus 1.
Plus okay, 1.5.
It becomes 1.5 because beta c is 1 here. So it becomes 0.5 plus 1. But what happens here is we have to restrict it to 1. It should be less than 1. That condition he has given. So this should be less than 1. So since you are getting more than 1, it is restricted to 1. Got it? This condition is there. So this value should be less than 1. Since you are getting more than 1, it has to be restricted to 1. So now shear strength of concrete Ks value is 1 now, and tau c value is also given in the same page here. Tau c is, he has given there 0.25 times root fc. 0.25 times root fc. This is tau c value. So 0.25 into root of 20. FCK is 20 here. M20 concrete is used. So it becomes how much? It becomes now
1.118.
1.118.
118.
Huh? M20 or M25 concrete? Oh, M25 concrete. You take it as M25.
Okay.
M20. Yeah. So take it as M25. So what is the value?
1.25.
ಇನ್ನೆಲ್ಲಾದ್ರೂ ಯೂಸ್ ಮಾಡಿದೀವಾ?
ಇಲ್ಲ.
M25 ಅಲ್ಲಿ ಇನ್ನೊಂದು ಕಡೆ ಯೂಸ್ ಮಾಡಿದ್ದೀವಿ ಆ್ಯಕ್ಚುಲಿ. We have used in that formula overall depth ಅಲ್ಲಿ 25 ಹಾಕೋಬೇಕು. So okay. So I think 25 ಹಾಕೊಂಡ್ರೆ ಎಷ್ಟು ಬರುತ್ತಲ್ಲ 141 ಬರ್ಬೋದು. Okay, it's okay. You can just take it up. So now this value is how much? 0.25 into root 25 is 1.25 alva? 1.25 Newton per mm square. But what is the nominal shear stress? Nominal shear stress is 0.88. Shear strength of concrete is greater than tau. So here you can observe that tau C is greater than tau. When tau C is greater than tau means tau B, you can call it as tau B. When tau C is greater than tau B, no shear reinforcement is required because concrete itself will take the shear. So you can see that shear strength of concrete is 1.25, whereas actual shear stress coming on the slab is 0.88. So strength of concrete is more than the shear. So therefore there is no need of providing shear reinforcement. So hence the slab is safe in punching shear. So slab is safe in punching shear. So this is how we have to check for here. Normally in most of the cases that shear check is done. Automatically it satisfies. So therefore no shear reinforcement is required. Usually slabs they don't carry more shear force. So shear reinforcement is not required here. Now the last step is reinforcement design. So design of reinforcement. For that you can use SP16. So SP16 so they will provide in the exam. So the directly you can see the chart and you can get the percentage. I will just give the one thing that I will explain how to calculate the reinforcement using SP16. Otherwise you have to use the equation. AST equation, you have to use quadratic equation you will get. In that two answers you are going to get. Out of that one value you have to take it as the reinforcement. But anyway, so I will take this next step, 7th step, reinforcement. Calculation of reinforcement. I will take actually how many reinforcements we have to provide here. We have to provide 4 types of reinforcements here because there are 4 values of moments. You can see, correct? 4 values in the area. So one by one we have to do here. So first one I will take up column strip. I will take in that column strip negative reinforcement I will do first. Okay, negative reinforcement. Correct. What is the value of moment there? Mu 205. Highest value
0.3.
Okay. Now I will tell you how to calculate the reinforcement using SP16. So you have to take this ratio mu by bd square. So I will do it by using SP16. So mu by bd square you have to take. Mu is 205.3 to 10 power 6 because we have to convert that to Newton millimeter. B is 3000. So column strip width is 3000 into D is 247. 249 I say. Effective depth of drop 249
249 is
20 plus
provided drop alva sir.
Provided
249.
249 3000 to 249 easiest one to take this ratio.
274.
274 in square d square. Table 3 of SP16 is what? What is the answer? Mu by bd square Hmm?
1.1037.
1.1037.
37.
Okay. 104 better. So for that value of mu by t square, SP16 in table 3, you will get directly the percentage of steel. SP16 ಸಿಗುತ್ತದೆ. So percentage of steel, here I can write it as 0.33%, 0.32%. The percentage of steel. Directly you can read from that table. You need not use that equation if you are using SP16. ಇದನ್ನ ಮತ್ತೆ page table 3 is page number 11. So you can just refer the table 3 of the SP16. ಈಗ ಇಲ್ಲಿ because it's a slab, you have to calculate the spacing of bars. Spacing beam only number of bars, slab only spacing of bars. So we have also 12 mm dia alva, we have also 12 mm dia. So first we calculate AST. What is the AST required? AST required is given by, so whatever PT is there divided by 100 into B into dm. This is AST formula. So 0.32 divided by 100 into 3000 into 241. So this will be in millimeter square. This is the AST required per meter length of this pipe. For 3 meters length of this pipe. What is the value?
2390.
2390.4.
90.4.
Okay, 2390. Now spacing required. Spacing of bars. 12 mm dia bars we are providing. 12 mm dia bars. So spacing required will be. So here, what is the area of 1 bar? Here the area of 1 bar is to ಏನು ಮಾಡಬೇಕಾಗುತ್ತೆ? ಏರಿಯಾ ಆಫ್ 1 ಬಾರ್ AS 5/4 into 12 square ಅಲ್ವಾ? ಎಷ್ಟು ಬರ್ತದೆ? ಏರಿಯಾ ಆಫ್ 1 ಬಾರ್
113.
113 millimeter square. ಈಗ ಹೆಂಗೆ ಕಂಡಿದೆ ಗೊತ್ತಾ? How to find spacing I will tell you. It is given by AS divided by AST. AS divided by AST into 3000. ಅಂದ್ರೆ into B. This is what is the formula, okay, for calculating spacing. So 2390, sorry, 113 divided by 2390 into 3000. This is the spacing.
141.
141 mm. Say 140. Got it? That means for this moment, negative moment, 205.3, we have to provide 12 mm dia bars at a spacing of 140 mm center to center. So this reinforcement is provided at the top, correct?
Yes.
Top of slab. Negative reinforcement top of slab. Hugging. Similarly, we have to calculate the reinforcement for positive bending. So same procedure is adopted. So I have taken first case like this. Similarly, second case will be column strip only, but positive bending moment. That is positive reinforcement. Correct? So mu by now, how much we have to take mu for this? So positive bending moment 88.4. Correct? 88.4 kilonewton per kilonewton meter. Same procedure is used here. So mu by bd square we have to calculate. So 88.4 into 10 power 6 divided by 3000 into 249 square. We are going to get one value. And we have to take from SP16 once again. From the table, we have to directly take the value of PT in percentage. Then assuming 12 mm dia bar, calculate the spacing. Got it? ಅರ್ಥ ಆಯ್ತಾ?
ಇದು 0.475 ಬರ್ತದೆ.
0.475 ಅಲ್ವಾ?
ಹಾಂ.
ಸೊ 0.475 ನೋಡಬೇಕು. ಅರ್ಥ ಆಯ್ತಾ?
ಟೇಬಲ್ 3 ಅಲ್ಲಿ.
ಟೇಬಲ್ 3 ನೋಡಬೇಕು. ವ್ಯಾಲ್ಯೂ ಅದು ಕಡಿಮೆ ಬರ್ತದೆ reinforcement because moment is less, you get reinforcement also less. ಗೊತ್ತಾಯ್ತಾ? ಸೊ ನಿಮ್ಗೆ ಇಲ್ಲಿ ಆಲ್ಮೋಸ್ಟ್ 400 mm ಸೆಂಟರ್ ಟು ಸೆಂಟರ್ ಆ ಥರ ಬರ್ತದೆ. ಓಕೆ, 240 mm center to center button. So now you can check it. So 12 mm diapass, so 240 mm, 240 center to center. PT ಬಂದು you may get roughly ಅಥವಾ ನೀವು ಇನ್ನೊಂದು ಥರ ಮಾಡ್ಬೋದು. ಓಕೆ, ಇದು ಪಿಕ್ಚರ್ನೇ ಮಾಡಿ BD ಮಿನಿಮಮ್ AST 3000 into 249 bottom line. Okay, so is it you have to do for middle strip also, but when you are doing for middle strip, what is the value of D we have to take for middle strip? Middle strip D change agutte. This is your middle strip. What is the total depth? Total depth is 215. ಅದರಲ್ಲಿ ಮೈನಸ್ ಮಾಡಬೇಕಲ್ಲ, effective depth you have to take. So I will write here fourth one, middle strip, negative reinforcement, positive reinforcement. ಅದು ಎರಡು ಬರುತ್ತೆ, ಕರೆಕ್ಟಾ? ಮಿಡಲ್ ಸ್ಟ್ರಿಪ್ ನಲ್ಲಿ ಎರಡು ಬರುತ್ತೆ, ಒಟ್ಟು 4 reinforcement ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. So third one I take it as middle strip. In that middle strip for negative reinforcement. So what is the negative reinforcement in middle strip?
68.4.
68.4 kilonewton meter. But here the value of D will be 215 minus 20 minus 12/2. Correct? 189 Okay. Depth is less here. So for that we have to take. So here B of course is same, 3000 mm. 3000 mm. So mu by BD square will be 68.4 into 10 power 6 divided by 3000 into 189 square. This is the value. Then once again from SP16 you get the value of PT, then AST, then spacing. Same procedure is repeated for middle strip for positive moment. So positive reinforcement, mu value will be defined. For that the mu value is 59 kilonewton meter. D will be same 189. B will be same 3000, width of middle strip. So in this case also we have to calculate mu by BD square, then get from SP16 the value of PT, AST and this is what the design is. So there are 4 types of reinforcements we are going to calculate, and one more last integrity reinforcement is also provided. I will tell you what is that integrity reinforcement. For that there is a simple formula. Only in case of flat slab we provide that integrity reinforcement. Integrity reinforcement AST is equal to, or AS is equal to 0.5 WU L1 L2 divided by 0.87 F1. This is integrated reinforcement. In this case 0.5 into WU is 18.56. They have calculated earlier. L1 and L2 they are equal here. 6 into 10 power 3, that is 6 meter span. In millimeters it is into 10 power 3. L2 is also same, divided by 0.87 into 400. F5 is 4. So this is the reinforcement required. We are going to get 925 millimeter square. 925 millimeter square. So 2 bars of 20 mm. 2 bars of 25 mm dia with of course with development length of 2 LD. With length of 2 LD, that is 2 into 1007. So all these this even if you don't write this, no problem. But in detailing, all these things are shown. Passing to the column cage. This passes through the column cage. Column cage in both ways, around both ways. So this completes the design of flat slab. So reinforcement sketch. If time is there, you can draw a simple sketch. Otherwise, you can leave. So anyway, there are 4 moments we have calculated, and for all the 4 moments, we have computed the reinforcement. So assuming same diameter of the bar, 12 mm diameter of the bar, only spacings will be different. Spacings will be different. So this is development length. So this is called as integrity reinforcement, which is provided as additional distinct for stability. So in reinforcement for strength, we are going to calculate the reinforcement using bending moment equation. For stability, of course, certain guidelines are there in the code. Based on that code, this is an additional reinforcement in the form of diameters. 2 bars of 25 mm diameter is provided throughout. That is for stability purpose. So this is how a flat slab is designed with drop. Okay.
1007
That actually it is there in the code. 1007 mm is the length of that. Of course, it is given in the code book. Of course, it is 1700 and 500 into 2. In that way, it is taken. Okay, there is an additional reinforcement we have taken. So this completes the design.